Okay, so like everyone, I love testing. It's great for other people to do. So I'm here to convince you that you should be doing more of it. And this is basically a very narrow topic talk. It is about failure path testing in C, and at least how I do it. There are several approaches, but I'll discuss this one. It's going to look like this. We're going to have a humble beginning, sort of where this idea came from. And for that, I will credit Jeremy Kerr, who is... Yes, there you go. And we'll go through sort of a simple example usage, and then we'll talk about the implementation, which is obviously interesting, more interesting for me than you, but it's my talk, so there. A couple of useful tricks, conclusion of future work, and of course time for questions at the end, but feel free to interrupt at any time and ask a question. Okay, so a long time ago, I think 10 years ago, Jeremy? Yeah, a long time ago, Jeremy and I worked on a project called NFSim. The idea was to take the net filter code, rip it out of the kernel into user space with sort of a user space framework, and run tests on it that were much, it's much easier to automate that kind of thing than it is to do it in the kernel. So you implement the kernel APIs and you create simple scripts to say, you insert this packet, this should happen. And that works reasonably well, but of course, you basically don't find any bugs doing that because that's just what the kernel does. What you do is you find bugs in your kernel API implementation and all that surround stuff, but you don't find any real bugs. But what we really want to do is test allocation failures. In the kernel, of course, you're not allowed to just explode when you run out of memory, so you have to handle and unwind all the state whenever there is an allocation failure. The problem with that is it never happens until it happens. So it never happens to you, it happens somewhere obscure to someone else. So, and worst of all, there are cases where you can actually deliberately trigger allocation failures, so people can use them for exploits. So it's actually very important to test that stuff in the kernel. And the trick that we did to test that in NFSim became failtest, which is now a CCAN module. It's a CCAN module because all my code these days is CCAN modules. So the CCAN module is called failtest, and that is the topic of the talk. Okay, so I'm going to jump straight in with a running example. So say this is your code that you want to test. We've implemented, for no particularly good reason, a string duplication function in C. So there isn't a huge amount of C code in here, but this is how you'd implement it. It hasn't been compiled, it probably works. So we don't conflict with the standard library, we've called it cstrudup. It's allocate and copy a string. Very, very simple code. So that's our function there, and in CCAN style, this would be the cstrudup module, and there's the file name. Okay, so we would write test code like this. Now, CCAN, one thing that we use for testing, which is a little unusual, is we actually raw include the .c source. That allows you to do a lot more special things in C. So rather than just being able to test at the link boundaries, you can then test static functions, you can reach inside and change behavior in your tests. So the way I prefer to write unit tests, at least, is to do it this way. And you basically just use the preprocessor to paste in the C code, possibly with some manipulation before and afterwards. So our test basically is a simple, this program will exit with 0 if it's all good. If something goes wrong, it will either crash or return 1. So we call our cstrudup function on the string hello. If it fails to allocate memory, we return 1, which is fail. If the string that we get back is not equal to hello, we fail. Otherwise, we free the string and return 0. So very, very simple test.
Are you happy for questions?
Yeah.
If you
a second question. No, only one each.
C file, can you still generate coverage information?
So if you include the hash C file, can you still generate coverage information? Certainly using something like gcov, yes. Because gcov amalgamates the results of all your running tests and runs them across all the files. You really need to do that for header files anyway. So there's no problem with generating coverage.
So the gcov GCDA file or whatever that's generated when you compile...
We'll refer back to the C file, yes.
Okay.
It knows the line number information. So that bit is all pretty straightforward. And debuggers similarly will jump to the right place. It all works actually surprisingly well. Generally considered incredibly bad form, of course, to hash include a C file. Okay, so that's very, very simple test case, right? So there's a unit test for our cstrudup function. Okay. Now you'll notice our test coverage there covered in green on a basic line-based coverage. We obviously haven't tested the return null allocation failure. Okay. Now, on a trivial example like this, that would actually be pretty easy to test. You'd override malloc. You would, run it again with your malloc set to please fail and do that. But this is just for the sake of example. Now, before I get into how you test for malloc failure, I do want to address this issue, which is an important one. And that is, there are actually remarkably few cases where testing for malloc failure is the most important thing in your project. For the kernel, yes, absolutely, it has to handle it. But sometimes a nice, clean core dump is the best thing you can do for your users. They either won't care, or if they do care, they will get a nice core dump and away they go. They can literally debug it. Particularly because untested code is buggy code. So it's very, very hard to test, even with techniques like this. It is very hard to get good coverage to test on all your allocation failures. It is almost impossible to write a significant program that handles allocation failures correctly. So if you're going to not handle it well anyway, just save yourself some typing and pain and another source of bugs and just let your program explode. The other point, of course, is there are other ways for out-of-memory to kill you. Yep.
What about optimistic memory allocation when malloc actually returns pointer even if you don't have enough physical memory?
There are other ways the OM to kill you. You can get a segv on stack growth, you can get segv on populating mmap, which could also include populating, which could include memory overcommit. You can turn off memory overcommit so that malloc only will return when you've got real memory, as a kernel-wide setting, for example. Most people don't, of course.
There's a problem with doing that too. If you're just, say, a database server, and so you're going to use like 30 gig of 32 gig of memory, but you then want to like fork an exec and like things in a nice little jail, you can no longer fork.
Yes. Yeah. There's a reason that nobody turns that on. But, you could get specialized and you could do that, but you'll have to rewrite all your software. So there are other ways the OM to kill you. One, of course, is that you'll get a seg fault when you actually try to access the memory that you thought you got back from malloc, which is basically segv on populating an mmap. You can also segv on stack growth. In theory, your stack could hit a certain point, the kernel goes, oh, you need another page, sorry, you can't have it, boom, you explode. Does your code handle that? Do you know how likely that is versus other methods of out of memory? It's a very good question. And of course, the OOM killer in the kernel could just decide we don't have enough memory, we're going to just shoot some people in the head. There's very little you can do about that either. Oh, that was the wrong button. Oh, wow. Oh, cool. Ooh. Mm.
Did you test the battery?
No, it's working on here. That's frozen in time. Let's try this again. Okay. We were here, we're here. Okay. So yeah. So basically, it is a bit of a losing game sometimes handling out of memory. Consider using malloc wrappers. There are two reasons for this. One is just to write a simple xmalloc style thing that just, prints out some diagnostic and kills your program, which is a little bit more friendly than a seg fault. A slightly more advanced version would try to do some emergency cleanup, might try to save the document before crashing, etc. That's sort of a best effort kind of thing. The other thing about writing your own malloc wrappers is you can write a new C++ style new wrapper that is type safe that will save you some real memory bugs. So consider using malloc wrappers or something like talloc or tal if you want to get more sophisticated. But the point of this talk is not so much to handle malloc failures, well, that's the most obvious thing. There are other conditions like writes failing on full disks and reads failing on closed file descriptors and things like that, partial reads, etc., to which this technique is also used. So I've used malloc here as an example. Doesn't necessarily mean it's a good idea to make your all your code malloc fail resistant. Okay, so how does it work? Well, basically what you do is you include failtest override.h, which looks vaguely like this, and basically includes the standard headers to get them out of the way, and then just overrides the definition of all the functions. And this, of course, means all malloc, realloc, calloc overrides free, and calls the failtest variants with file and line information. So it's basically failtest override.h is this long header that basically overrides all these core functions that it wants to test. Because you include this before you include your C file, this overrides all the ones in your code, so your code that you're testing doesn't change. but actually it's doing something completely different now. We also have a failtest undo.h if you want your original ones back, that will basically not quite undefine them all. And then there's a failtest.h, which actually contains the control functions to control the failure testing. So we take our example and we add the headers here. We add failtest override, then we include our C file, and then we add failtest undo and failtest. And we run failtest init, and instead of exiting or returning 1, we use failtest exit. And that there will test that malloc failure path. So it's a pretty straightforward transformation to your test driver framework to test your failure paths. And that's the appeal of something like failtest. Except for when, of course, some of the heuristics go wrong and it actually introduces more failures. But if you do, say you didn't handle, I did it again. Okay, so every time I hit the volume thing on the side, I get unitied. So, so by the end of this, I will have given this talk about 4 times. Okay, so you'll get a message like this, killed by signal 11, which is a seg fault, to reproduce dash dash failpath equals, and a whole KISS line of letters. Each letter represents a separate call that we trapped. M is malloc, W is write, etc. in failtest. The capitals are the ones that we forced to fail. So you can see here that we failed the first malloc, we allowed the second write, and we failed the third write. And then you feed that back into your test program. Failtest init, you may have noticed, takes argc and argv, so it can pull those out again, and goes, okay, this time that's the path we want to go down. So you just run that on the debugger, and you can see when it injects those failures exactly what happens, and find out how your program dies. How does this actually work? How do we do the magic? Well, our implementation of replacing all the functions actually forks your program. This was Jeremy's brilliant insight, that rather than do all this fakery, we can basically overload fork because it does all the copy on write stuff we want. Most of the stuff will just be duplicated for us by the operating system. So if we just fork and run stuff in the child, after the child exits, the parent will be back where it started. So the child runs the failure path, because the child is the one that's almost certainly going to die with a seg fault or some horrible thing. So we want that. Oh, I just need to wait. Am I impatient? Okay. Patience. So the child is the one that actually runs the failure path, and the parent continues. Now the parent will actually wait for the child. The child should reach a fail path exit. Anything else is considered that something went wrong. That's a weird design decision that I'm kind of reconsidering. Perhaps it's not a bad idea. But there may be code in your test path that you end up actually doing a manual exit. And I wanted to check that you didn't get to those. So for the moment, you have to get to a fail test exit path for your child to have considered to have not failed. So obviously, if your child seg faults pretty much it's always a seg fault. Does something horribly destructive. Yeah.
Could you implement that with a glibc destructor?
I could implement it with a glibc destructor. The reason not to do that is, at the moment, I really did want to trap people using exit. And it works for my code. So it's possible that when we get more examples of people using things, it may turn out to be a bad idea and we should just use exit. We could override exit, right, which would work too. Now, it doesn't matter what the exit status is. In fact, it should be non-zero. If you inject an error, you expect your test to fail. That's okay. The child can fail, but it must not die. It must not explode. So, of course, you're thinking combinatorial explosion. If we fail run down every path where we fail every test, we're going to get this, we've got 10 tests, that's 1,024 different possibilities. That combinatorial explosion doesn't quite happen because most tests fail fast. Most tests, once you inject a failure, they'll fail and die and fall off the planet. In fact, you noticed in our test driver, if something failed, we just called failtest exit immediately. So we didn't run the rest of the test. So if you design your test that way, it works pretty well. If it doesn't fail fast, it's probably an imprecise test. So for example, if you said, I expect this write to fail, and you go, oh, that's good, and I'll continue with my test, and we inject a failure and make your right fail anyway, now you'll be running two, the parent and the child. You do that a few times, you will get combinatorial explosion. That's a bad test. Your test should be, I expect this right to fail with this error number. More precise test means that then the child has had an injected failure, you will catch that. So where we found that tests don't fail fast, it's almost certainly because it's a badly written test. So it does help locate those. Now, we do have some heuristics to stop this. If you write code like this while you're looping, of course, if we just keep injecting failures, we'll go forever because you'll keep trying to malloc. So we actually record the backtrace, the stack pointer. So we basically have a call trace of where we hit the failure that we injected, and the second time if we ever get back to that on the same child failure path, we don't inject a second failure. Now that's a compromise between coverage, because it might actually be nice to inject a failure at the same place twice, and performance. So simple heuristic, we've seen the backtrace before, we don't go there again. And this is a special heuristic to not inject open failures where the open would fail anyway, because you're basically double testing. There's a lot of programs that open some file that may not be there. They expect an enoent, they expect to go on and fall through to something else. So we check before we do the open, go, oh, hold on, this is going to fail anyway. Let's not inject a failure and have both the parent and child fail, because that will explode. Okay, now it's not quite as simple as fork and the child will be merry, because the child may actually do stuff. Programs are like that. It may truncate, write, or touch anything in an MMAT file. So the parent actually just saves the contents of all the open files and restores them afterwards. It's not that efficient, but it works surprisingly well. The child may actually read from a file and move the file pointer offsets, and because Unix is interesting, we share those with our parent, so the parent also has to restore file offsets. The child, of course, is expected to will often spew stuff out to standard out and standard error. If you just let all that go through, you'll get many copies, because all the children will write stuff out to standard out and standard error, and you get the same thing over and over again. So what we do is we actually capture standard out and standard error in the parent for the child spewing out, and we only ever bother spitting it out should there actually be a failure down that path, so you can see what happened to the child if it printed something out. Now, for NTDB testing, particularly I added this. The child may add and remove file control locks. It turns out to be kind of hairy to do that because the parent will actually be holding them and the child expects to be holding them. So we have a mechanism by where it asks the parent, can I have the locks please? And it hands the locks down to the child. When the child does, it tries to reacquire them. That, of course, is racy because you can't hand someone a lock. You actually have to drop it and they grab it. So if we had a really complicated test, you could end up failing. But it works for the test that we have at the moment. So, okay. Now, of course, the child may actually unlink a file, or because we only save the file descriptors that we have open, the child may open a file, change it, and close it again. We don't handle that. You will discover that if you use -- trace, which will show you everything all the children are doing. When you discover that mysteriously when you run things under failtest, it fails in weird, weird ways.
Could you intercept the open in the child and just
Yes.
log, hey, this has happened, you probably need to fix that?
We could, although most opens are innocuous. So in practice, it's kind of like this. Really, I mean, what we should be doing is intercepting open in the child, reporting to the parent, hey, by the way, we're, add this to the list of things to restore. And, I mean, a simple matter of code, but it hasn't been done because we haven't run into it in practice. I'm mentioning it here so that when you do run into it, you know. GetPid obviously is going to return the wrong value for the child. Similarly, getppid, signals, etc., will all be horribly, horribly wrong. At some point that should be done. I look forward to your patches. Now, of course, remember I said before you shouldn't be worrying too much about malloc failures anyway. So what if you don't want to fail malloc? Well, we have a hook called failtest hook. And you can basically, at every point, get the history of all the calls that have occurred and return one of various results. Fail, don't fail, which says actually don't bother injecting a failure here. Fail OK, which means yes, you can inject a failure here. And actually fail probe. You'll only ever get one fail probe in a call chain. There are some times where, and this was more common before you had the backtrace heuristic, there are some times where you don't want to go too far down a garden path. So you go, okay, fail this once, but the second time I return fail test probe, don't keep going down that path. So fail test probe is basically a fail once. So there are 3 results you can return rather than just a bool. So here we say, basically, we've got this linked list of the history, we grab the tail, and if it's a malloc, a calloc, or a realloc, we don't ever fail it. So that solves things pretty nicely. Okay. The power of Valgrind. Okay, now, you can run the whole thing under Valgrind, of course, and this is incredibly powerful because there's often things that happen, especially in failure paths, is you end up with use after free bugs. Valgrind will pop on those immediately. And with the right arguments to Valgrind, you can tell Valgrind to have an error exit code on the child, which means nfsim will go, the child exited with status 127, and here's the call path. Because debugging forking processes is such a pain, you then put that fail test equals blah massive string into GDB, run it again, it'll run down that specific thing, and you can see exactly the path that it takes to leak things. In fact, fail test, because it has to track a whole heap of this stuff for various reasons, also does its own leak reporting too, even if you don't run it under Valgrind. Now, if you care about memory leaks on failure paths, and similarly file descriptor leaks, which is also useful, you have to turn that on in Valgrind to say you really care. The fail test network infrastructure itself is quite careful to clean up in fail test exit, so it doesn't leave any allocations lying around. But your test infrastructure will also need to free up any mallocs if you want this to work, so you don't leave stuff lying around, even in those failure paths. But if you've got your test code clean, and fail test is already clean, then you will actually find leaks that happen on failure paths in the code you're testing. So that can be incredibly useful, and I run it under Valgrind. That's how I do it. Okay, now on any fail test exit call, you get this hook that's called, and the best example of this is probably in the NTDB code. So this is a test for the NTDB. Oh crap, no that isn't. Yeah, how do I do this? Let's guess. Is it over to the right? Yes, it is. Go. I have. Again. Now, how do I get that over there? Okay. Stay. Stay. Okay, I've got that over now. Drag. Excellent. Okay, so here, let's be ambitious. Let's try to widen this as well.
Can you make the text bigger?
No. I already did. Nope. Shift left click, huh? Oh, wow. Shift left click. Increase buffer text size. Okay, change buffer font, increase. Let's try this one. Did that work? Once. You can only increase it once. You said increase, you didn't say by a useful amount. Okay. So importantly, this runs, basically it runs NTDB open with a whole heaps of different flags and everything else. Now, if NTDB open, which does a whole heap of stuff, if it fails, then it just immediately exits. That's fine with the exit status, which is from the TAP framework, which says whether or not something failed. Basically goes around and around and around. So this is the important point. NTDB open actually does quite a lot of stuff. Opens the database, checks it's the right format. If necessary, if the flags are right, creates it. Does all these things. We want to inject failures in there. We want to inject failure like a write failure. We want to inject an open failure, etc., etc. So we're using fail test here, obviously, because the fail test override. We don't fail test undo because we don't do any mallocs or writes or anything in here, so we don't need to undo it. So we include this. Now, we set fail test hook to block repeat failures. That we used to go through the history and look for repeats and refuse to fail twice. Actually, this predates the backtrace, so we don't need that anymore. But fail test exit check says exit check log. And if you look at exit check log, which is in failtest.helper.c, this is exit check log. So every time a child exits, it's handed the whole history of all the calls that failed and didn't fail, whatever happened. So it goes through the history, and if it didn't fail, ignore it. Now, there's a couple of places in the code where we try to open files that may not exist, like dev random. That's fine, we handle that. If we can't get randomness from there, we fall back. So, and importantly, we don't log. Similarly, so random read, if that fails, again, we go, okay, well, we'll use something else. And the very first malloc that we do, which is kind of ugly, the very first malloc we do, that can fail, we won't get a log message out because we can't malloc. And of course, if we do non-blocking functional locks, we can expect those to fail, so the code, again, will not log. But for anything else, if we injected a failure of any other kind, we expect a log message. In fact, at one stage, we used to insist that there only be one log message. That turned out to be a little bit hard to enforce, so we loosened it. This exit test checks that if we injected a failure, ignoring a couple of cases that we know about, there must be a log message. Tap log messages is basically a count of how many messages that we output that is implemented elsewhere. So this exit test is incredibly important because it means that for NTDB, unlike TDB, there are no silent failures. If anything in our code fails that we don't expect, we will get a log message out, and this guarantees it. So that's what the exit check is for, and it's incredibly important. Okay, so now I'm going to try to restore ourselves to across here. Okay, 5. Are there any questions on that, by the way, before I lose it? Okay. Okay. Undoing side effects. Unlink. Okay, follow this exit check. Excellent. Some results. Okay. So in NFSim, and so these results are slightly old, but it gives you an idea. Our test coverage was 61%. Now that's a simple GCOV style line count. That's not really test coverage in any accurate sense, but it gives you an idea. We had 61%. When we implemented failtest with the forking and everything else, we went to 65%. Woo! Okay. And the thing to take away from this is writing more tests is almost certainly more effective than adding failtest. But failtest is 1, easy, and 2, it will get that last few percent, which may well be important. So first, get your coverage way above 61%, get some reasonable amount of coverage, and then tack failtest on the end. So when you get tired of actually writing tests, failtest gives you that little boost. And that's really where it's most effective. Okay, so I want to talk about a little bit of future work. I want to have user-defined failure tests. Sometimes you have a routine of yours and you want to be able to just inject a failure in that. So say, when you call that, I want to inject a failure. It shouldn't be too hard to implement that. So you can basically, at the beginning of your test driver, say, here's a couple of functions, I'm going to override them, and here's telling failtest about it. That's pretty straightforward to add, it just hasn't been done. And that will make failtest much more usable for your own projects. So you can say, okay, I have this complicated routine, sometimes I just want the whole thing to fail, return null, or whatever it does on failure. That's also important because there are cases that aren't really failures that I'd also like to cover. For example, short writes or short reads. The classic thing is to assume that when you read from something, you're going to get the whole amount that you asked for or hit end of file. But if what you're reading from is actually not a normal file, and is a pipe, for example, you will expect to get short reads at sometimes. And it's amazingly common that programs don't handle that well. Now, those cases are not failures. Whether you get the whole buffer or a small buffer is not a failure as such. So you will get combinatorial explosion with that. If you test both paths, you're going to explode, right? So it would be nice to be able to do that in some limited way, either by you saying, actually, for my writes, always return 1 byte at a time, just to see what happens. Or for my reads, just do 1 byte at a time. So if we added our own internal function registration system, we could get rid of that. And of course, there's an infinite arms race to cover more and more calls and more weird side effects. So the child can do an almost infinite amount of things to the parent that will go wrong. So as we encounter them, we tend to do whack-a-mole and go, okay, well, let's implement that properly and simulate that. And that's an infinite race, so we know we'll never finish it. So I'm being completely driven by when people go, hey, I'm trying to do this and this doesn't work. And that's how we do NFSim, do the others. Okay, that, in record time, is the end of my talk. Are there any questions? Yes?
Have you had any thoughts on how you're going to implement TCP tracing?
TCP tracing, yes, no. Another question? Yeah.
You presented here an example where you actually instrument.
Yeah.
What was your experience with the effect of the simple fact that you're running an instrumented program compared to running it naked? The kind of problems that either pop up due to that or are not discovered because of it?
Okay, interesting. So the question on instrumented versus uninstrumented. So the main problem we saw was performance. So I'd have to rerun this. The NFSim tests ran in something like 3 seconds. That went to 7.5 minutes when we ran it under fail test. Now, the heuristic, that's why the heuristics are more aggressive now. They used to let you fail in the same place for 3 times, for example. Now we do backtrace and stuff, that's probably cut down, but you're still talking seconds to minutes.
I'm looking beyond.
Then run the whole thing under Valgrind and talk hours, 18.5 hours to run it. So that was the main blocker. So whereas looking at side effects that you might get from running on this infrastructure.
Timing issues rather than just slowness.
Yes. So
Races.
for my stuff, I didn't hit, because we're talking about unit tests, they tend not to be as sensitive to timing issues because that's kind of going beyond a single unit test when you've got complex timing issues. More what we saw with the problems of the infrastructure that is simulating some of these things is overly simplistic. And you're actually running in a child and it does introduce some differences. And those were the problems that we generally saw. Hopefully they're all now fixed, but it's whack-a-mole again.
Have you looked at implementing, FreeBSD has an infrastructure called fail points, where you can inject failure points into functions in the kernel and turn them on and off.
Ooh.
So have you looked at actually implementing this stuff in the kernel directly?
No, I haven't. I haven't looked at failure points. I think that's really interesting. It's more useful when you've got a binary rather than you're dealing on the source code level. I like failing at malloc rather than failing at sbreak, for example, because that tests what I care about. So we're one level up. And the same way, for example, you do a strut up here, you won't get an injected failure because I don't wrap strut up. I could, or I could just implement the user one so the user can wrap strut up if they want. There is a benefit in it wrapping one level higher than the kernel. Now that said, injecting failure points in the kernel is a great way to stress things.
The reason we use it at Isilon is because we have an enormous amount of in-kernel file system code that we need to test.
Yeah.
And so we need to be able to provoke certain failures to make sure that things get handled.
Yeah. So the other thing with with fail test is we try to avoid having to annotate places where you want to fail. And I wanted to automate all that. Now you saw the reverse where I had to annotate in my testing code. I had to animate places where we're allowed to fail without logging, for example. That turned out to be a slightly lesser evil, I think. But yeah, for some code bases, I've done it manually and had to annotate. You can fail here and things. I like this if you can do it. Yep, last question.
How do you handle, or do you handle stuff where you have a master-child process relationship already? Think Apache multiprocess, think in my particular point of interest, PostgreSQL.
We did in NFSim because we had an IP chains binary actually on the other side, and we'd fork the binary on the other side of the pipe and have it track 2 of them, but it was very specific to that solution, and I haven't tried to do anything more generic. I look forward to your patches. Okay. That's it for questions. Thank you, Stuart.